All right, in this section, or this part of the section anyways, we're looking at some properties of logarithms. In the first half of this video, or in the first section here, section 3, we looked at what a logarithm was, how to use logarithms to kind of rearrange exponential functions and use that to solve for variables. We looked at how it was the inverse of an exponential function and how we could use that, or attempt to use that anyways, to solve for x and solve for different variables. We're going to start this one by looking at some properties of logarithms. I'll let you pause it and write all these down. And then we're going to do some examples. So one property of logarithms is very useful. If you are taking the log with any base, doesn't matter, the logarithm of two numbers being multiplied together, we can expand that to the log, the base stays the same the whole time, the log of the first one plus the log of the second one. And I mentioned this when I talked about the history of one of the places where logarithms were commonly used was if you were multiplying big numbers together. So that'd be like what we have here. If you have one big number times another big number, multiplying two big numbers without a calculator is tedious, it's slow, and it's prone to error. So one thing that people would do is they would take the log of both of those numbers and add those numbers together. And that's what this property gives us here, is it says that the log of x plus the log of y is the same as the log of x times y. So you can use this property to expand multiplication and to combine two logarithms with the same base being added together is the same as x times y. Division, same idea except with subtraction. If you are dividing two numbers within a logarithm, so the log of x divided by y, we can expand that or separate that out into the log of x minus the log of y. This should feel a little bit like properties of exponents, where when you multiply two powers together that have the same base, you can add the exponents. Kind of the same idea here, where if you're multiplying two numbers within a logarithm, you can add the log of those two numbers separately, and vice versa. One thing I want to mention is it does not work to say that the log of x plus y is the same as the log of x plus the log of y. Note, this addition between the two logarithms does not mean it's x plus y here. Don't make that common mistake. You can't separate the log of x plus y. Doesn't work, so don't try it. A third property, and this one we're going to use quite a bit as well, says that if we have the log base b of x to the r power, so something to the something power, one very useful tool that logarithms allow us to do is to take that exponent and essentially pull it down in front. And so instead of log base b of x to the r power, it's whatever that power was, r, times the log of x. And so we can essentially get rid of the power altogether. So if we're trying to solve for that exponent, if we're trying to solve for r, this allows us to bring that exponent out and make it into multiplication instead of a power. And that's going to be really useful. And we're going to look at an example of that in just a little bit. So write that down. Okay. One type of problem that you'll be asked to do on a test and on a quiz is to use those properties to expand things out. So if I'm giving you a logarithm right here, log base 10 of 8xy over 3z, you might be asked to expand this as much as possible into as many logarithms as you can. So instead of having it in one neat package, we're looking at expanding it out and blowing it up. So when we do that, one of the properties that we can use right away says that if you're dividing, we can take whatever the numerator is minus whatever the denominator is. So we can take the log base 10 of 8xy, instead of divided by 3z, it becomes minus log base 10 of 3z. So we can take the numerator minus the denominator and separate it with these logarithms. From there, we had a property that says if you're multiplying within that logarithm, log base 10 of 8 times x times y, we can expand that out into the log base 10 of 8 plus the log base 10 of x plus the log base 10 of y. So we can expand that out further. We can take that 8 times x times y and make that into plus log of x plus log of y. One thing I want to mention is right here. This minus log of 3z didn't become minus log of 3 plus the log of z. Because we're dividing by 3 and dividing by z, it's minus 3 and minus z. It's almost as if that minus sign was being distributed. We're subtracting the log base 10 of 3, and we're subtracting the log base 10 of z. And so that minus sign is being distributed amongst the 3 and the z there. And you could draw parentheses, I guess, if you needed to. But basically, what you need to remember is if there's more than one thing in the denominator here being multiplied together, 3 times z, it's going to be minus both of them because they're both being divided. They're both in the denominator. So that would be the expanded version of this. Give this one a try on your own. See if you can expand this out. I put some exponents in there. So you're going to have to go back and look at this property, property 3. So all 3 properties are included in this problem. Give this one a try. I'm going to put the answer up. If you have no idea if that square root throws you, watch a follow-up video on how to do it. That's the solution. If you go, oh, I get it, great. If you're still going, huh? Watch the follow-up video, and I'll show you how to separate that out. You'll also be asked to work the other direction. So on a homework assignment quiz test, I'm going to give you the expanded version, and I'm going to ask you to put it all together. So we need to be able to take things apart and put them back together again. We have this expanded version of a logarithm. I want you to use all those properties to put this into one single logarithm. Put it all into one nice package. I'm assuming you paused it. If you didn't, pause it, try it on your own. I'm assuming you tried this. Again, give it a shot. Even if you get stuck, it's better to try it first before you watch me do it. It encourages you to do the thinking and not rely on me to do the thinking for you. This is the solution. If you did not get that solution, or if you have no idea where it came from, watch the follow-up video. I will point out that this dot here is not necessary, but I wanted to separate that this is y to the 8th power times the cubed root of x divided by w, or all over w. Okay, moving on. Let's do some examples of solving. If we had this problem, 7 equals 3 to the x power. I have no idea what that would be because 3 to the second power is 9, but this doesn't help in this problem. Okay, so if we use the properties of logarithms, we could rearrange this a little bit. We could say log base 3 of 7 equals x, and that's true. That's correct. There's nothing wrong with that. However, we can't use a calculator because that's the log base 3 instead of the log base 10. So that still doesn't quite get us the answer. We have to do this a different way. So we've got 7 equals 3 to the x power. I've just rewritten the problem. One thing we can do to help us with this, and this is where we're going to pull on that third property of logarithms. That third property of logarithms allowed us to work with this exponent in a different way. So if we take the log base 10 of both sides, I chose log base 10 because I can use a calculator with that. So that common logarithm, the log base 10, I can use a calculator. It's effective for me. I could have chosen log base 4, but that doesn't mean anything for my calculator. So I'm going to choose log base 10. I did the same thing to both sides. So there's nothing, I haven't broken any rules of algebra here. Log base 10 of 7 and log base 10 of 3 to the x. The reason that that's effective, the reason I would do that at all, is now I can use that third property of exponents, or third property of logarithms, which says I can take this exponent here and I can pull it down front. I get this. So that log base 10 of 3 to the x power, I can rewrite that as x times log base 10 of 3. Remember that log base 10 of 3 is just a number. It's some decimal. And you can plug that into a calculator, log base 10 of 3. Log base 10 of 7 is just some number. It's a decimal number. So what I have here is I have a decimal equals x times a decimal. I can solve that pretty easily. If it's x times some number, I can divide both sides by log base 10 of 3. I divide both sides by log base 10 of 3. This is a decimal divided by a decimal, and you can plug that into a calculator. Works out to be this. Just to show that, I think I have a calculator up here. I don't. Let me pull it up really quick. This is my calculator emulator. So if I have, again, log, so the logarithm button is right here, log base 10 of 7 divided by the log base 10 of 3, I get that. So by using the log, by taking the log of both sides, I can use that property that says I can pull that x down front and make it into x times the log base 10 of 3. I can divide both sides by the log base 10 of 3 and get the result. And that, using that property allows me to solve new problems. All right, let's look at another example of this. Suppose I deposit $12,000 into an account with an annual interest rate of 6% compounded quarterly. Compound interest is coming back to this problem now. To the nearest tenth of a year, I don't know how many years it will take for the account to have $2,400 in it. So I'm going to use my formula. The formula was A equals the principal, P. Principal was the amount that I deposited or invested, $12,000. 1 plus the rate, which in this case was 6%, so 0.06 in this formula. Compounded quarterly, so divided by 4, and is 4 in this case, to the power of 4 times t. T is time. That's what I don't know. I know that I want to have $2,400 in the end, so I've got my compound interest formula filled in. Let's try and do some solving. One thing I can do is I could combine the 1 plus 0. I could do this bit in parentheses here and get this, 1 plus 0.15. So I can do some arithmetic there. Remember, I can't multiply these together yet. If I follow my order of operations, I need to do the exponent first. So I can't do that. I could divide both sides by 1,200, because this is 1,200 times something. So I could divide both sides by 1,200. I would get 2 equals 1.015 to the 4t. I've done as much simplification as I can. Now I need to deal with this exponent. This should look similar to the one we were just doing, where I had, I think it was what, 3 to the x power equals 7. Very similar problem now. I can address this by taking the logarithm base 10. I'm choosing base 10 for the calculator. Logarithm of both sides. So if I take the log base 10 of both sides of that equal sign, so nothing else changed, I just took the log base 10, I can use that property number 3 of logarithms, which allows me to take this exponent 4t and bring it down front. Now I expanded the 4t to 4 times t, but I just put a dot. That's the only thing I changed. So I pulled that 4t down. That allows me to use my normal rules of algebra now, where I've got all multiplication here. I've got a number, log base 10 of 2 is a number 4, my variable t, and a number. So log base 10 of 1.015 is just a really complicated way of writing one number. If I have all this multiplication here and I want to get t by itself, if I want to get t by itself, I can divide both sides by 4, and I can divide both sides by the log base 10 of 1.015. So I'm going to divide both sides to get rid of this t, or to get t all by itself, to isolate that variable. So if I divide both sides by log base 10 of 1.015, that divides to 1. I can divide both sides by 4. 4 divided by 4 is 1. So I can divide those numbers away. Since it's multiplication, I can divide. That'll leave me with just t left over. So I'm dividing both sides by 4. I'm dividing both sides by log base 10 of 1.015. And if you type this in your calculator, you get this. And the decimal keeps on going. The problem said to the nearest tenth of a year, so it'd be about 11.6 years, a little over a year and a half. And that's how long it would take. Just to show it with the calculator to make sure that this isn't a problem. If I use the calculator, I get log of 2. Again, I choose base 10, so I can use a calculator. Divided by, when you're using this TI calculator, to plug this in, this calculator is going to want parentheses. 4 times the log, again, base 10 of 1.015. So I am putting parentheses around that, and I'm 99% sure that it needs it. And there's my answer. So make sure you put parentheses there. Okay, almost done. I know this is kind of a long one. There's that. So we can solve now a whole new problem with our compound interest formula. I'm going to ask you to try these two on your own, solving the equation. Use the properties of logarithms that we've been looking over. Combine things together, rearrange things, see if you can't get x all by itself. I know this is going to be stretching what we've done. I haven't done any examples of these yet, but I've done examples of all the tools you need. So you've seen examples of everything you need to know to solve these problems. It's just putting them all together and being creative with those properties. So try it. If you don't get the right answer, watch the follow-up videos, and I will walk through it step by step. Here are the solutions. Again, if you're completely lost or if you got close but you're still not sure why you got the wrong answer, watch the follow-up video.